Okay. So electromagnetic induction. So in that first topic, I will tell you what is magnetic flux. What was electric flux? Number of electric field lines passing through. Number of electric field lines passing through a given area. That was okay. Number of electric field lines passing through a given area, that was electric flux. So this is magnetic flux. Magnetic flux means the number of magnetic field lines passing through a given area or a surface. That is magnetic flux. What is the formula for electric flux? E dot A. Okay, E a cos theta. Similarly, magnetic flux formula will be, instead of electric field here, magnetic field. Magnetic field is B dot A. Same. Okay. So magnetic flux is B dot A. Okay. And is it a scalar or a vector? Scalar or vector? Electric flux was scalar, right? It is a number of field lines. So magnetic flux is also a scalar quantity. It just gives a number of field lines. Okay. So if the area is like this, and if the magnetic field is like this, what will be the flux? Flux will be cos 0 will come. Cos 0 is 1. So it will be just BA. Now, if the area vector is like this, and if the magnetic field is making an angle theta, flux will be BA cos theta. Okay, clear, right? So that is about magnetic flux. First we will write magnetic flux. So write magnetic flux. Magnetic flux. It is the total number of magnetic field lines It's the total number of magnetic field lines. It is the total number of magnetic field lines crossing through any surface. Crossing through any surface. Normally. It is the total number of magnetic field lines crossing through any surface. Normally. When it is placed in a magnetic field. When it is placed in a magnetic field. Equation you write. Phi B is equal to B dot A. Phi B is equal to B dot A. Phi B is equal to B dot A. It is a scalar quantity. It is a scalar quantity. What will be the unit? Tesla, meter square or Weber. WEBER. So it is a scalar quantity. Unit will be Tesla, meter square or Weber. Unit will be Tesla, meter square or Weber. Then just draw these two diagrams as well. You wrote the equation, right? Phi is equal to B dot A. Write the equation. It is a scalar quantity. Unit is Tesla, meter square or Weber. Then you write the diagram. Here theta is equal to 0 degrees, so phi is equal to BA. Here phi will be equal to BA cos theta. Okay. Now, next give side heading electromagnetic induction.
1 minute.
Yeah.
Ma'am, can you read out the diagram I need to copy?
What?
Ma'am, I need to copy the diagram.
You didn't copy?
Not the first one. Yeah, I need to copy the first one.
You did you copy this?
That's the only one.
Yeah, Lakshmi, did you copy the second diagram?
Ma'am,
Okay. Give heading electromagnetic induction. Electromagnetic induction. Okay, now listen, okay. The electromagnetic induction means, see, just imagine this is a conducting coil. A conductor, listen all of you. Listen. Okay. So this is a conducting coil, okay. A copper coil wound in the form of a, copper is a conductor, right? So a copper coil wound in the form of what you can say, solenoids or something. So a copper coil, and this is a magnet. Okay. So if you bring this magnet near to the coil, an EMF will be induced in the coil. Okay. Lakshmi, can you hear me properly? Because you seems to be stuck.
yeah, ma'am, it's lagging.
Okay. So if you have a coil, conducting coil, and if you bring a magnet towards the coil, there will be an EMF developed in the coil. Similarly, if you take the magnet away from the coil, EMF will be induced in the coil. Okay. You fix the magnet. If you move the coil also, EMF will be induced in the coil. So basically what happens is, whenever there is a relative motion between a conducting coil and a magnet, an EMF will be induced in the coil. Whenever there is a relative motion between the coil and a magnet, an EMF will be induced in the coil. Okay. And if that coil is in a closed circuit, if the coil is in a closed circuit, due to that EMF, current will be produced. And that current we call it as induced current. Current will be produced only if it is in a closed circuit. Otherwise, EMF will just generate and it will just go. Understood? So whenever there is a relative motion between a coil and a magnet, an EMF will be generated in the coil. And if the coil is forming a closed circuit, the current will be produced. And that current we call it as induced current. Understood? So basically, what happens when you are moving this coil? See, around the magnet, there is magnetic field line. Okay, so if you move this coil, means the magnet, if the coil is here, the coil will have only less number of field lines. When you bring the coil towards the magnet, the number of field lines associated with the coil is changing. What do you mean by number of field lines? Flux. Okay, so when you bring the coil towards the magnet, the flux associated with the coil is changing. When you move the coil away, also flux associated with the coil is changing. So in simple words, what you can say, whenever there is a change in flux associated with the coil, due to any reason it could be. Okay, whenever there is a change in magnetic flux in a coil, EMF will be induced in the coil. And that EMF will produce a current. And that phenomena is known as electromagnetic induction. Okay, due to change in flux, EMF is induced. That is electromagnetic induction. Clear? Understood? Any understood? Huh? Okay.
Yes,
So, yeah. So write it in 3 terms. Okay, 3 points you can write. So write, when there is a relative motion, when there is a relative motion, when there is a relative motion between a magnet and a coil, when there is a relative motion between a magnet and a coil. When there is a relative motion between a magnet and a coil, then an EMF is induced in the coil. Then an EMF is induced in the coil and is called induced EMF and is called as induced EMF. An EMF is induced in the coil and is called as induced EMF. Okay. If the coil is closed, if the coil is closed, if the coil is closed,
Yes.
if coil is closed, then current flows through the coil. If coil is closed, then current flows through the coil and is known as induced current.
Can you repeat? I was in the washroom, the first thing.
Leave space, Lakshmi. You can write later. If coil is forming closed circuit, then electric current is in. What did I say? If the coil is forming a closed circuit, then current flows through the coil and it is known as induced current. It is known as induced current. Done, right? Okay. Now I'll just explain the diagram. I'll draw four diagrams. Okay, just to explain this point. But okay, I'll tell you. So this is a north pole coming towards a coil. So as I told you, if the north pole is coming towards, current will be produced, right? Current will be induced. Okay, current will be induced. EMF will be produced and current will be induced. Okay, and the direction of current is explained using another phenomena. That also I'll just add here. I'll explain. If it is not clear, don't worry. When we study that topic, we will be doing it again. Okay. Now just, when north pole is coming, current will be induced. That is clear, right? Now what will be the direction of current? Okay. So if north pole is coming towards the coil, see, if the teacher is planning to take a class 10 minutes extra, what you will do? You will leave the meeting or you will attract or you will repel? Repel, right? Same. If north pole is coming towards the coil will repel north pole. How the coil repel north pole? By inducing north. By inducing north. So north means anti-clockwise. Okay. So the current induced will be in anti-clockwise direction. There is a law to explain this. When the north pole is coming, the coil repels and all. So that we will study later. So now you just understand, if north pole is coming, current is induced. Clear? Okay. Now if north pole is leaving, if the north pole is leaving, if the north pole is leaving, the coil will again oppose that. It won't allow the north pole to leave. So what will be created here? South. So what will be the direction? Clockwise. The current produced will be clockwise. Understood? Okay. So if north pole is coming towards the coil will repel north pole. Whatever is the cause for inducing EMF, that will be opposed. The cause will be opposed. Here what is the cause? North pole is coming is the cause. So it will repel the cause by inducing a north and repelling the north pole. Here what is the cause? North pole leaving is the cause. So leaving is the cause. So the coil will try to hold north pole. It will always try to oppose the cause. So for holding north pole, south will be created. So south means it will be clockwise. Understood? Similarly with south pole, can you try? So if south pole is trying to reach near the coil, what will happen? South will be induced, right? South means what? Clockwise. So the current induced will be clockwise. And if the south pole is planning to leave, it will try to hold south pole by inducing a north pole, that is anti-clockwise. Clear? Now, if it is clockwise, if the galvanometer is deflecting that side, anti-clockwise, it will deflect left. Okay, so if this is anti-clockwise, if it is deflecting right, for clockwise, it will deflect left. So this is again clockwise, right? Deflecting left, anti-clockwise, deflect right. Okay, so this is a galvanometer. So when, as I told you, whenever the magnet is coming towards or away from the coil, current will be induced, and that time galvanometer will show the deflection. That's it. Now, can you just tell me, if I keep the magnet inside the coil, will current be induced? No. I'm keeping the magnet inside the coil. Will current be induced? No. There should be relative motion. Okay, yeah. There should be a relative motion between the magnet and coil. Then only current will be induced. Clear, right? Clear. Okay, so draw these 4 diagrams. Draw the diagrams first. Done? What?
Anti-clockwise and clockwise symbols are like open, right? They're not like closed cycles.
No. I just north means it will be anti-clockwise. Just to understand that, I wrote. You are asking about the alphabet.
No,
Then
no.
what?
The symbol anti-clockwise, clockwise symbols.
It is closed only, right? It is only a closed circuit, right?
Arrow, the arrow is on the opposite.
This is clockwise, right?
Huh?
This one. I know, just south means it is. I just want you to understand. Here, south pole, right? South pole means it will be clockwise. With S, you can make. With south means it will be clockwise. North means it is anti-clockwise. Huh. No. This is just from the alphabet I was just telling you. I just want you to understand. South pole means it always produces a clockwise current. This is not required, okay? Just for you to understand, I told. I thought you studied this in 10th, right? No? Okay. See, south pole means it always creates a clockwise current. It is easy to remember like that. North pole means it always creates an anti-clockwise current. Anti-clockwise, right? That is what I there is nothing to do here. Oh. Okay. Got it, right? Okay. So now just one more sentence, okay? All of you finished? Okay. So just one more sentence you write. Whenever the magnetic flux, whenever the magnetic flux, whenever the magnetic flux linked with a coil changes, whenever the magnetic flux linked with a coil changes, an EMF is induced in the coil. Whenever the magnetic flux linked with a coil changes, whenever the magnetic flux linked with a coil changes, an EMF is induced in the coil. Whenever the magnetic flux linked with a coil changes, an EMF is induced in the coil. Whenever the magnetic flux linked with the coil changes, an EMF is induced in the coil. This process is known as electromagnetic induction. This process is called electromagnetic induction. This process is called electromagnetic induction. Clear, right? Okay. So if they ask electromagnetic induction, if it is for 1 mark or 2 mark, just this much is enough actually. Okay. Whenever there is a change in magnetic flux, that is what I said, right? See, actually, if there is a coil, and if a magnet is bringing near to the coil, what is basically happening? The magnetic field lines associated with the coil is changing. Okay, whenever a magnet is brought near or taken away from a coil, the magnetic flux associated with the coil is changing. As a result, an EMF is induced. That phenomena is known as electromagnetic induction. Clear? Okay. Now, we will do 2 laws. Okay, you have Faraday's laws of magnetic induction. Same thing what we have studied. So write Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. There are 2 laws. Faraday's law of electromagnetic induction. First law. There are 2 laws. First law. First law. Whenever the amount of magnetic flux, whenever the amount of magnetic flux, whenever the amount of magnetic flux linked with a circuit changes, whenever the amount of magnetic flux linked with a circuit changes, whenever the magnetic flux linked with a circuit changes, an EMF is induced in it. Whenever the amount of magnetic flux linked with the circuit changes, an EMF is induced in it. That is first law. Now second law. This one we studied only, right? Whenever the amount of magnetic flux linked with the circuit changes, an EMF is induced in it. That is the first law. Now second law. Second law. The magnitude of induced EMF in a circuit, the magnitude of induced EMF in a circuit the magnitude of induced EMF in a circuit is equal to the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux is equal to the rate of change of magnetic flux. Okay, so the magnitude of induced EMF in a circuit is equal to rate of change of magnetic flux. How will you represent rate of change of something? Divided by T or d by dt. Okay, d by dt. Okay, so induced, yeah, d by dt. Yeah, Rehan. So induced EMF is equal to what? D by dt of what? Magnetic flux. Okay, so this is the formula given by the second law of Faraday. Faraday's like second law. Induced EMF is equal to rate of change of magnetic flux. Now, I will put a negative sign also. Why? Because we already studied, right? When I explained, I told you. The induced EMF always opposes the cause. So for that, we will put a negative sign. Okay, that is a separate law that we'll be studying next. Okay, so now you just write the equation also. E is equal to minus d phi by dt. Write the equation. E is equal to, in school you took E or small e or capital letter, the normal E. This one only. Anything is fine, okay. So induced EMF E is equal to minus d phi by dt. If there are n number of turns, if there are n number of turns, what will happen? N phi will come, right? So if there are n number of turns, E is equal to minus d by dt of n phi. So n you will take outside. E is equal to minus n d phi by dt. If there are n number of turns, EMF will be equal to minus n d phi by dt. Okay, the negative sign indicates that the negative sign indicates that the direction of induced EMF, negative sign indicates that the direction of induced EMF is such that the negative sign indicates that the direction of induced EMF is such that it always opposes the change in magnetic flux. It always opposes the change in magnetic flux. Correct, right? Whatever be the cause which resulting in the change in magnetic flux, it will be opposed by the induced EMF. Correct, right? Okay. So now
Ma'am,
we'll
can
do.
you repeat?
Yeah. How much you wrote, Ananya?
Induced EMF is
Such that it always opposes the change in magnetic flux. Such that it always opposes the change in magnetic flux. Write a problem. The magnetic flux linked with a loop is given by the magnetic flux linked with the loop is given by phi is equal to 6t square plus 7t plus 1. Magnetic flux linked with the loop is given by phi is equal to 6t square plus 7t plus 1. What will be the EMF induced? What will be the EMF induced at t is equal to 2 seconds? What will be the EMF induced at t is equal to 2 seconds? Yeah. Try to do. How to do? E is equal to d phi by dt. Who is non-math? You know differentiation? Okay. See, those who have math you do, others listen. D by,
Minus d phi by dt.
yeah, you have to do that like that, that's it. Okay, so d by dx of x raised to n, the formula is n into x raised to n minus 1. That is the formula for differentiation. Okay. N into x raised to n minus 1. Okay, now here if you apply, no, n into x raised to n minus 1. Integration is x raised to n plus 1 by n plus 1. So EMF will be, you have to differentiate each term. Here with respect to time, right? d phi by dt. So each term I will put it inside d by dt of what 6t square plus d by dt of 7t plus d by dt of 1. Now 6t square, right? So this is in the form x raised to n. This is in the form x raised to n. Okay, so it will be 2 into t raised to 2 minus 1. Into 6 will come. Okay, 6 into 2 into t raised to 2 minus 1. Okay, plus 7 into, this is t raised to 1 already. 1 into t raised to 1 minus 1. Plus differential of a constant is 0. Differential of a constant is always 0. So it will be 12t plus 7. T raised to 0. Anything raised to 0 is what? 1. Anything raised to 0 is 1. So 12 EMF at t is equal to 2 seconds is what they are asking, right? EMF at t is equal to 2 seconds. So now when you put t is equal to 2 seconds, you will get 12 into 2 plus 7. So it will be 31 volt.
Now, what about the negative sign?
If you didn't put negative sign also it is fine. If you put also it is okay. It is correct only. The negative sign always shows the induced EMF opposes the cause.
Yes.
Okay, Bhavya. If you put negative without putting negative was also correct. Negative sign shows it is opposing the cause. EMF, right? We are not finding phi. It's not, you thought Weber. Did you do? You were sleeping? At home before coming for tuition? Finished, right? Okay. So that is about now we'll do few problems, okay? Did we write Lenz's law? No. Okay. So next is Lenz's law. Next heading, Lenz's law. Ananya, you have maths, Ananya?
No, ma'am.
You understood this?
Yeah, I know basic.
Okay. Vardhan? Understood this, Vardhan?
Yeah, ma'am, differentiation.
You have maths? Vardhan is having maths? Oh, okay. Okay. Now, Lenz's law. Lenz's law. Write the statement, okay. According to this,
Faraday is only one law.
Faraday, 2 laws. I gave 2 laws. You wrote only one.
Okay. No, I think I didn't read the heading for it.
Second law is the magnitude of induced EMF in a
Yeah,
circuit. You wrote?
Yeah.
Okay, Lenz's law. Next is Lenz's law. According to this law, the polarity of induced EMF, is such that according to this law, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produces it. According to this law, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux which produces it. Tends to produce a current which opposes the change in magnetic flux that produces it. Done, right? I'll explain. Before that, you tell me. There is a north pole coming towards a coil. What will be the direction of induced current in the coil? Tell me what will be the direction of induced current in the coil. All of you tell me. So, Amina, what do you all say? Fauzia, Ananya? Clockwise. Fauzia,
Yes, ma'am.
what will be the direction of induced current in the coil?
Anti-clockwise.
Rehan, Lakshmi? See, North Pole is coming. North Pole is coming towards the coil. So, the coil will oppose. Okay, so opposing North Pole means what will be created? North Pole will be created. North Pole means what? Anti-clockwise. Okay, so the induced current will be anti-clockwise. Now, if South Pole is moving away from the coil, Adib, tell me. If South Pole is going away from the coil. So here what should be created? North. It will try to attract. So it will be north. North means again anti-clockwise, right? Correct. Now you know the concept. So let us read the statement. According to the statement for Lenz's law. According to this law, the polarity of induced EMF is such that it produces a current. So EMF is induced and it produced a current. According to this law, the polarity of induced EMF is such that it produces a current which opposes the change in magnetic flux which produces it. So here magnet coming is the cause. So induced current is opposing that cause. That is the meaning. Okay. So you can, by hearting is not easy. So understand like this and learn. According to this law, the induced EMF is such that it produces a current which opposes the magnetic flux which produces it. Clear, right? Law is clear? Okay. Yeah, tell me, who can say the law without looking? See, according to this law, in the induced EMF try to produce a current, okay, which opposes the cause which produces it. Yeah, Jayana.
Me?
Mm.
The induced EMF is such that the current.
It produces a
It
current.
produces-
According to this law, the induced EMF is such that it produces a current,
It produces a current that opposes the magnetic field.
magnetic flux which produces it.
Magnetic.
Okay, Joel.
According to this law, the induced EMF is such that produces a magnetic flux.
No, it produces a current, induced current. EMF is such that it produces what? It produces a current such that it opposes the flux that produces it. Then Ephraim.
The according to this law,
According to this law,
the EMF
induced EMF is such that
the current
it produces a
It
current.
produces-
EMF produces a current.
Yeah.
According to this law, induced EMF is such that it produces a current
is opposite.
which opposes the
Opposes
magnetic flux that produces it. Ishanvi.
The induced EMF produces an induced current, which opposes the change in magnetic flux which produces.
Yeah, correct. Adi.
This law, induced, the polarity of induced EMF is such that it produces a current which opposes the change in magnetic flux which is produced by
Which produced it.
Yes.
Okay, clear, right? Okay. So draw the diagram also.
This is a diagram for
The lenses law.
this one.
Yeah. Without diagram also it is fine, but just draw the diagram. Nowadays teachers are cutting marks with less explanation, okay? If you're not writing more explanations, they will cut marks. Done, right? Okay, now we'll do a few problems based on this. No. For that, law of conservation of mechanical.
Induced current is anti-clockwise.
Here, in both cases, it is anti-clockwise.
Induced current.
Okay. Now, basically, from Lenz's law, they will ask you to write the law and explain the conservation law of this Lenz's law actually obeys law of conservation of energy. They will ask a question like this: state Lenz's law and explain how it obeys law of conservation of energy. It is basically here the magnet is moved towards the coil. The magnet is moved towards the coil. So I'm doing some mechanical work. So that mechanical energy is converted to electrical energy. So we know energy can either be created or be destroyed. So here I am doing some mechanical work for moving this magnet. So that mechanical work energy or mechanical work is converted to electrical energy. Now the magnet is kept ideal. I'm not doing any mechanical work. Is there any current produced? No. So likewise, Lenz's law obeys law of conservation of energy. Okay. Is converted into electrical energy. Yeah. Some laws will be there in the form of heat or something. Yeah.
Law of conservation of energy.
No. Lenz's law, next side heading, Lenz's law follow law of conservation of energy. Then we'll write the statement below that. Lenz's law follow law of conservation of energy. Lenz's law follow law of conservation of energy. Lenz's law follow law of conservation of energy. Okay, below that you can write The mechanical work done in moving a magnet. The mechanical work done in moving a magnet the mechanical work done in moving a magnet with respect to the coil mechanical work done in moving a magnet with respect to the coil changes into electrical energy and produces current. Changes into electrical energy and produces current. Okay, changes into electrical energy and produces current. Hence, energy transformation is taking place. Hence, energy transformation is taking place. Hence, energy transformation is taking place. When we do not move the magnet, work done is zero. When we do not move the magnet, work done is zero. Hence, induced current is also zero. When we do not move the magnet, work done is zero. Hence, induced current is also zero. Therefore, Lenz's law obey law of conservation of energy. Therefore, Lenz's law obey law of conservation of energy. Hence, energy transformation is taking place when we do not move the magnet. Work done is zero. Induced current is also zero. Therefore, Lenz's law obey law of conservation of energy. Done, right? Okay. Now we will do a few problems. These direction questions, okay? So first question. In the given figure, predict the polarities of. In the given figure, predict what? Yes.
Can I leave? I have exam tomorrow.
Yeah. Okay.
Yes.
In the given figure, predict the polarities of plates A and B.
In given figure,
In the given figure, predict the polarities of plates A and B of the capacitor. It's a capacitor. Capacitor will have a positive and negative, right? One plate is positive plate, another plate is negative plate. Okay. So always current flows from positive to negative. So like that. You just need to find the current induced, what will be the direction. Accordingly, you can predict. Try. See here, North pole is coming towards the loop. So what will be created here? North, anti-clockwise. So anti-clockwise means it is like this. So it starts from positive and negative. So it is anti-clockwise. So current starts from here, right? Current starts from A to B. Current always moves from a positive to negative plate. So A is positive and B is negative. Got it, right? Okay. So you can write the answer. North pole is induced. So current is anti-clockwise. North pole is induced. So current is anti-clockwise. Therefore A is positive and B is negative. North pole is induced. Current is anti-clockwise. Therefore A positive and B negative. Then right. Next question. The electric current flowing in the direction. The electric current flowing in the direction B to A is decreasing. The electric current flowing in the direction B to A is decreasing. Find direction of current induced in the loop. The electric current flowing in the direction B to A is decreasing. Find the direction of current induced in the loop given. Okay, I'll explain. So there are two ways of explanation. If it is an MCQ, the first explanation, you just need the answer for MCQ. The first explanation is enough. But if it is coming as a 2 mark or 3 mark, it won't be coming as a 3 mark and all. But in case if they're asking for 2 and 3, you should give proper explanation. That time you can use a second explanation. The first explanation is like, so we know as per Lenz's law, whatever be the cause, whatever be the cause, yeah, yes, Rehan, whatever be the cause, the induced current will oppose it. Here, what is the cause? Current decreasing from, or current decreases towards A, or current is decreasing towards left. That is the cause. Current decreasing towards left is the cause. So the induced current in the loop will try to increase current towards left. So increase current towards left means like this. Understood. Here the cause was decreasing current towards left. So the loop will try to increase current towards left. So it will be clockwise. That's the easy explanation. This you cannot write for a 2 mark question. This you can use for only for MCQ. This explanation is easy only. You understood, right? The second explanation, B to A current is decreasing. That means towards left current is decreasing. Towards, the question is like that.
Oh, okay.
So here current is decreasing is the cause. If the current is steady, will EMF be induced? Will current be induced? No. The current is changing. That's why current is induced in the neighboring room. Okay. So current decreasing. So if the current induced in the loop was in the opposite direction, current towards left will further decrease. So in order to increase the current towards left, current has to be induced in the same direction. Clear? Now the proper explanation. This is clear, right? Okay. Now, here current from B to A is decreasing. B to A current is decreasing. Then, in this loop, what will be the direction of magnetic field due to this current? In this loop, the direction of magnetic field will be into the page. This is the current. Adib, listen. This is the current. Magnetic field will be into the page in the loop. So current decreasing means magnetic field into the page is decreasing. Correct, right, Ishanvi? Okay. So magnetic field into the page is decreasing. That is the cause. So how to oppose the cause? By increasing magnetic field into the page direction. Okay. So magnetic field into the page is decreasing. So as a result, what will happen? Into the page magnetic field should be increased. So increasing magnetic field in the into the page direction, what is the current? Clockwise. Okay. Therefore, current induced will be in the clockwise direction. Understood? Clear? Okay, this explanation is what you need to.
Magnetic field is into the page, right?
Yes, yes. See, here current is decreasing from B to A. So due to the B to A current, magnetic field on this loop is into the page, direction is into the page. Current decreasing, so into the page magnetic field also decreasing. Okay, so as per Lenz's law, if the magnetic field is decreasing, it should be opposed. How?
Okay.
You have to increase the induced current will try to increase magnetic field. In which direction? Into the page magnetic field decreasing.
Okay.
So we have to increase the magnetic field. In which direction? Same direction. See, here magnetic field was 10 Tesla. It is going down. It decreases to 5 Tesla. How can you increase it? By adding more magnetic field in the into the page direction itself. If you put like this, net magnetic field decreases, right? So into the page magnetic field also should be increased. So here into the page magnetic field is decreasing. So you have to increase the into the page magnetic field. How will you increase into the page magnetic field? Into the page means current will be what? Clockwise. By inducing current in the clockwise direction, into the page magnetic field will be increased. Understood? Clear? Okay, do this one. You can note the explanation, okay? So this is the answer. I'll give the explanation, right? Here, B to A current decreases. Here, B to A current decreases. Here, B to A current decreases. So the loop try to increase the current. So the loop try to increase the current. Therefore, as per Lenz's law, induced current will be in clockwise direction. Therefore, as per Lenz's law, induced current will be in clockwise direction. Therefore, as per Lenz's law, induced current will be in clockwise direction. Therefore, as per Lenz's law, induced current will be in the clockwise direction. Done, right? Okay. Now, same question. Same question, okay. The diagram only differs. Find the direction of induced current in loop 1 and 2. Current B to A is decreasing. The question, you write it as a separate question. Current from B to A is decreasing. Find the direction of induced current in loop 1 and 2. Find the direction of induced current in loop 1 and 2.
One is local, you to anti-local.
Yes. Yeah, Rehan, correct. Okay, so B2 it is decreasing, right? So both loops will try to increase current towards left. Okay, so this will be clockwise and this will be anti-clockwise. Okay, got it right? Okay. Now, next is, yeah, one more question. Write a question. A current carrying solenoid. See, listen, this type of question, lot of questions are there, okay? Normally in MCQs they used to ask, okay? Lot of questions are there. So, like it will take maybe 5-6 days to finish set of questions. So every day, until we finish this chapter, every day when you come, I will give few questions. Then when we do regular practice, it will be okay. Okay. Now, a current carrying solenoid is moved towards a current carrying solenoid is moved towards a conducting loop as shown. A current carrying solenoid is moved towards a conducting loop as shown. What will be the direction of induced current in the loop? What will be the direction of induced current in the loop? What will be the direction of induced current in the loop? Yes. How to do?
Anti-clockwise.
Why anti-clockwise?
Because it goes back.
Huh?
Because it's entering the
Okay. So,
from
what is here?
the
North pole. Why it is North pole?
anti.
You're looking from that side. When you look from that side, it is anti-clockwise. When you're looking from that side, it is anti-clockwise. If I look from this side, it is clockwise. Okay. Huh? See, this is clockwise for me and for you it is anti-clockwise. For me it is clockwise. Correct, right? For me it is clockwise. What is this direction for you? Anti-clockwise. Same. Okay. So it will come like this. If you have a loop like that, always it will be there. Okay. So clockwise, anti-clockwise, there will be a confusion. For this one, for me it is, if we look from this side, it is clockwise. If you look from the other side, it will be anti-clockwise. So if you're looking from that side, what your answer is correct. So when you write the answer, you should specify. Better you specify.
But entering from the towards the right.
Ah, that is okay. But if this is north, then only it is valid, right? Okay. Okay. So, but if I look from here, this is south. That is what I said. So looking from right or looking from left, that you should mention. Normally they will mention in the question or they will draw an eye or something. Okay. So here if you are taking this as north, then here also it will be north and then it will be anti-clockwise. That is when you look from this side. Correct, right? Okay. So, on looking from right, when looking from right, induced current will be anti-clockwise. Rehan, the thing is, here when you look from the right, this appears to be north. But if you look from the left, it appears to be south. If this is south, then induced will be south, right, Rehan? Understood the difference? Okay.
Anti-clockwise, right? If you're looking from the right.
Yeah, from the right, the north is coming towards the loop, right? So it will be. Finished, right? That is done. Okay. There are a lot of questions like this that we will be doing later. When you get time, you can try to do. In your textbook exercise, the first question has 8 diagrams. Okay, 8 diagrams. If I start explaining that, one full class is not enough. That much confusing it is. Okay, so you can try doing that first 8 questions on the textbook. After doing a lot of questions, I see like there's so many things you have to consider when you do those questions. 8 questions or something. 1, 2, 3, 4, 5, 6, 7 questions. 7 figures are there. So a lot of points will come when you try to identify the direction of current. Okay, they are just asking us to find the direction of current in all the loops. That's what they are asking. So after doing a lot of questions, we will do those. Okay, if you can easily do those, then paka. Khalas. Then this topic will be done. Okay, now next topic is motional EMF. You have to take your textbook. Topic 6, there is a diagram. You have to copy the diagram. 6.6, I think. Motional EMF. Figure 6.6, you don't have textbook. Anybody else? All of you have? You have? No? Only one? Okay. I'll give. Yeah, I'll give. That diagram. No. The down 6.6. What figure is that? Huh? Figure 610. Under the topic, motional EMF. So this figure is what you have to copy. Okay, this one. This figure you have to copy. Yeah, I'll pass. Pass. This one, yeah? Yeah. Mega fell asleep. Mega was sleeping. Let's see what happens. Finished? Today everyone is sleeping. One of my 11th grader also. When I called, no response. When her mother called, no response. Now she woke up. Theory is there. So first I'll explain, then I'll give the theory, then you need to do the derivation. 3-4 steps only, easy only. See, this is motional EMF. Motional EMF, this one you will have to apply when something is moving, a rod is moving in uniform electromagnetic field. Then you will apply this. Something is moving in uniform magnetic field. Okay, Earth is having a magnetic field, right? Earth is having a magnetic field. So any conductor moves in a magnetic field like this, EMF will be induced. So what about the flights? The wings of the flights are there. It's a conductor. So it is moving in Earth's magnetic field. So will there be EMF induced? Yes or no? No?
Yes.
Yes? Are we using the EMF? Why? Huh? What? What happened? You will get shocked. That's what you're saying. Oh. See, something moving in a magnetic field, definitely EMF is induced. In flight also, EMF is induced in the wings because wings is going like this in in magnetic field. But that wings is not forming a closed loop. If it is forming closed loop, then only it can be harnessed. Otherwise, it will just go. Understood? So, anything moving in a magnetic field, EMF is induced. So, we are going to find what will be that EMF. Till now, we studied EMF is induced due to change in flux. Here, a rod moving in a magnetic field. Here there is no magnet, nothing. This rod is moving in a magnetic field. This conducting rod is moving in a magnetic field with a velocity V. What will be the EMF induced? That is what we are going to study. Okay, so I'll just write the derivation. No need to do it now. I'll give the theory, then only you need to write. So EMF induced is minus d phi by dt, right? Correct? So here flux will be what? B into area, right? B is uniform. What will be the area? Area will be, this rod is moving. This rod length is L and the distance is X. Okay, so L into X will be the area. Okay, in that L is a constant, X only will be changing. Okay, so for area, you can write it as minus d by dt of what? B into L into X, correct? L into X is area. B, L are constants. Magnetic field and length of the rod is constant. I will take it outside. Okay, so minus B into L dx by dt. What is dx by dt? Velocity. So minus B, L, V will be the induced EMF. If you have a rod of length L moving with velocity V in a uniform magnetic field, the induced EMF will be given by BLV. Again, the negative sign has the same meaning. It is opposing the cause. Even if you didn't put the negative, it is correct. If you put also, it is correct. So for a safer side, what you can do is, the negative sign shows the induced EMF is opposing the cause. Okay. It will be 0. Okay. So, right. Consider a rectangular frame MSRN. Consider a rectangular frame MSRN
Our cos theta people.
because area vector direction and magnetic field direction is same. Okay. Consider a rectangular frame MSRN in which the conductor PQ is moved perpendicular to magnetic field. In which the conductor PQ is moved perpendicular to magnetic field. So the magnetic flux associated with PQRS. So the magnetic flux associated with PQRS. So the magnetic flux associated with PQRS, phi is equal to BA. Phi is equal to BA, which is equal to B into L into X. Phi is equal to BA, which is equal to BLX. As PQ moves, as PQ moves, the flux changes. As PQ moves, the flux changes. Hence, EMF will be induced. As PQ moves, flux changes. Hence, EMF will be induced. Induced EMF, then write the derivation. Induced EMF E is equal to. Okay, done, right? Derivation is okay. Now we have one more derivation related to this topic itself. See here, this one finished, right? Here the rod was moving straight. Instead of that, if the rod is fixed at one point, there is uniform magnetic field. The rod is fixed at one point and it is rotated. If the rod is rotated in a magnetic field, what will be the EMF produced? Okay, it is not moving like this, it is rotating with the angular velocity omega. Then what will be the EMF induced? That's what we are going to study next. Okay, so heading you can give expression for EMF between center and the metallic rod. Expression for EMF between the center and the metallic rod. So the same textbook, turn one page, you have example 6.6. Example, what question is that example? Same under the topic, what's the example question number?
6.6.
6.6. In the 6.6 next page there is a diagram. In the example 6.6 there is a diagram. Copy that diagram. The circle one, yes. Done? Finish, right? Okay. So listen, if this rod is rotating, it makes an angle theta. Okay. So here if the rod is rotating, the area, uniform magnetic field only, area is what is changing. So if the rod initially is at OP, then it rotated till OQ, this will be the area. If it rotated till here, the area is changing. Okay. So here area in this sector, what will be the area enclosed in this sector? Any idea? The total area is pi r square. Correct, right? Total area of the circle is, this is r, right? Pi r square. Area of OPQ, how will you find the area of a sector?
Omega by T.
No.
Um,
How will you find?
Omega equity.
Theta by 2 pi into pi r square. Total area is pi r square. The area of the sector is theta by 2 pi into pi r square. When you do, you will get the area of the sector. Theta is the small angle. By 2 pi is the total angle. Into pi r square you do, you will get the area of the sector. Okay. So theta by 2 pi into pi r square, if you do, you will get the sector area. So it is r square theta by 2. Got it? Okay, don't write. Okay, theory is there. So now here also EMF induced will be what? Minus d phi by dt. So phi is what? BA, right? Minus d by dt of BA. So for B I will take outside, and for area I will substitute that. Okay. So minus B d by dt of r square theta by 2. R square is common. It's constant. It's the radius of the rod. And 2 also I will take outside. Only theta is there. So minus b r square by 2. What is d theta by dt? Omega. So minus b r square omega by 2 will be the expression for induced EMF in case of a rotating rod. What? No. It is taken as 90 degree. That's why. Okay. Got it, right? Okay. So, right. A metallic rod of length R. You finish the diagram, right? Finish the diagram? Yeah. After that, you write a metallic rod of length R. A metallic rod of length R is rotated with angular frequency omega. Is rotated with angular frequency omega with one end fixed at the center. With one end fixed at the center. With one end fixed at the center. And it is rotated in a region of uniform magnetic field. And it is rotated in a region of uniform magnetic field. And it is rotated in a region of uniform magnetic field. Let theta be the angle between let theta be the angle between two positions P and Q. Two positions P and Q in time T. Let theta be the angle between two positions P and Q in time t. Here area OPQ. Here area OPQ equals OPQ equal to you write that area of OPQ theta by 2 pi into pi r square. Write this area of OPQ equal to theta by 2 pi into pi r square, which is equal to r square theta by 2. Done, right? Therefore, induced EMF. So in the textbook, is negative given in the formulas? No, right? No, right? See, if you don't write the negative also, it is correct only. So you can neglect the negative sign, okay? You can neglect the negative sign.
Only that for direction.
Yeah, it is just for the direction. So E is equal to d phi by dt. So d by dt of dBA. So for A, you will substitute that. So in textbook, two methods are given. I have given the second method. Okay, first method is integration. Second method derivation I have given. Okay, done, right? Finished. Derivation done. Okay. So, next class will. So actually, half of the chapter is over. Okay, but we have not done any questions. Like the direction questions, as I told you, like 1, 2 full class. If you take only, that will be over. So that I will give in small doses. I will give. Okay, and this one. See, when you get the question, you should identify whether it is motional EMF or not. How? If a rod is moving with a velocity, then it will be motional EMF, BLV formula. Okay. If a rod is rotated, for example, they will tell you, like in the tire, the car or bike tire, you have seen a rim, right? The rim is the outer layer above which we will fix the tire. Rim and spokes are there.
Ma'am, can I leave? I also have lab exam.
Okay, Lakshmi. Which subject you have?
Physics.
Leave fast. Yeah, so this is these are the spokes actually. Okay, and this is the rim. Okay, so if a rim with spokes rotated in magnetic field, the same thing. So here, let us assume 5 spokes are there. So what will be the total EMF?
Right, she's
What will be the total EMF? So basically, this center and this thing, it is a parallel connection. Can you imagine it as parallel connection? So you have 2 rims like this. See? No, it won't work. Hello? Yes. Yes. Yeah. Okay. Yeah. Can I call you like in 10 minutes? Yes. Yeah. Okay. Yeah. See, this will be in parallel connection. Why? Because this is the center and this is the outer layer, right? Okay. So this outer layer and this center. Here the potential will be the same. Let it be A. And here it is B, right? All these spokes are connected between A and B. That means it is parallel connection. In parallel, EMF is the same. So if you have 100 spokes also, the EMF induced will be the same. You just need to do BR square omega by 2. If they are 10 or 1, the EMF will be the same. You don't have to multiply because it is in parallel connection. Understood, right? Clear? Okay. So next class, we will do few questions from the based on lenses law. Then we will start inductance. Under inductance, you have what is inductance, then self-induction and mutual induction, only 2 topics. So that I will finish in 1.5 class, then this chapter will be over. And only problems will be left. Okay. Okay then. Bye all of you. Yeah. Bye Vardhan. Bye Rehan. Yeah, bye. Samananda, where are you staying?